Well, so first I will like to thank all of you for inviting me here. Okay, so this is actually, well, I mean, I wanted to give this talk, but this is actually not, well, not exactly, probably not in work in progress, but writing in progress or some such thing actually. Yeah, so there may be some things which may not, well, I mean, okay, so let me start with this thing. So there was a very nice paper by this Prohar and Daniel Capek. This, well, I think the archive number is something like 17, 11, 04371. Okay, so this paper is called D-dimensional stress tensor for Minkowski d plus 2 gravity. But, well, I mean, there are soft photons and all these things are there actually. Okay, so in this paper, so what they basically try to do was to write the soft, well, so writing the soft theorem as, so we know that there is this relation between soft theorem, and then it gives you the word identity for asymptotic symmetries or symmetries, whatever. Okay, so in particular, if you have soft photon, so it gives you, for example, an infinite dimensional E1 global symmetry. So roughly the way you can think of this is that, so this is the null infinity, well, so this is the Penrose diagram of the Minkowski space, and what you can do is that you can take a two-dimensional, so this is supposing 4D, but this is actually at least true in any even dimension. So you can, so let's just talk about the 4D case now. So you can take a cross section. So this cross section is a sphere, okay? And then there is a, so this is actually basically it's a large gauge transformation. Okay, so under which, so it is something like say A mu, well, or say AA or AZ or something. So ZZ bar are coordinates for the S2. So this is very schematic actually, but I think this will just give you the, so something like this, some transformations like this. So this phi ZZ bar, so that's a function on the S2. Okay, and you can think of the, if you have some say charge scalar field or something, then it actually gives you some transformation like say phi going to e to the power IE. Okay, so these phi there, say, okay, phi e to the power IE, phi ZZ bar, phi. Okay, some such things. Okay, so that is the, oh, you are here. Okay, so this is the infinite dimensional global symmetry, but well, I mean, this is very schematic. So I think you are, well, I mean, you must have heard many talks on this. So I just wanted to tell you, I mean, well, for yeah. Yeah, right. So these thing actually, so the coordinates along this is like u, and then you have this ZZ bar, but this thing actually does not depend on either. So this is just a function on the sphere. Okay, so that's the idea. Okay, so this is actually this is the simplest case, and now let me actually write down this thing. So now let me write down the soft theorem. So the and then I have some bunch of operators. So these are basically the, so this is an S matrix, okay, OI, EI, and these are say scalars, okay. So these are like creation, annihilation operators. So something like OA, and then I have some bunch of say OI equals say 1 to n out, and then some J equals 1 to n dagger in okay. So this is just a shorthand notation for that. So this I runs over all these out creation and out annihilation and the in creation operators. Okay. So this now the point is that, so if you now take U0.
Sorry, the in and outs are defined on scribe minus and scribe plus, right? Effectively.
Yeah, so this is just the standard S matrix. So here we are not talking about scribe plus, scribe minus. So this is just a standard S matrix actually. So we are not writing it as some correlation function between scribe plus and scribe minus. So this is just a standard S matrix. Yeah, it is massless actually, and you can actually write it in terms of this scribe plus, scribe minus here. But the point is that
the standard LSD sort of.
Yeah. I mean all the same. This is very standard. Actually, okay. And yeah, so this is actually a photon. Okay, and these are actually some charge scalars. Say, okay. So you have an so this is some charge scalar, and this is just an outgoing photon, okay, and which we finally take to be soft. Okay, so that is the. Well, I mean, if you can take them to be massless or massive, but I'll be so I'll be working with massless scalars, okay. Because the massive case is more complicated actually, because the particles don't reach. I mean, there is a, they'll reach the what is called I0 or something. Yeah. So if you now take this Q0 going to 0 limit, so this thing actually factorizes. So this is the soft factorization. So this is I equals 1 to n. J by, and then we have this. So this is the soft factor, okay. So okay, and now what you can do is that so there is a 1 over q here. So what you do is that you can take so I will use a particular, so all these things are actually massless. So let me use this particular parameterization, that p mu I write as omega 1 plus x square 2x.
Yeah. Quoting a known soft theorem.
Yeah, it's known. I mean, well, I mean, this is the, sorry, yeah, this is the Weinberg theorem. Actually, yeah. Well, I mean, yeah, but I mean, you just assume that they are massless. Yeah, right. I mean, some such thing is there actually. Assume that thing holds actually. No. I mean, I think the thing is that I mean, well, just well. So, for, well, I mean, if you are unhappy about this, let's take this to be the tree level. Actually, I mean, you can just take them to be the tree level. But the point is that I think, yeah. So I mean, those things are there, but I mean, whether such a theory exists or not, but well, I mean, somehow, let's assume that such a thing is there. No, this is actually exact to all loops. I mean, this factorization. Huh?
It doesn't matter what the particle matter or not.
Yeah, but he is asking something else actually. So he is asking that, I mean, how do you know that these are, I mean, these, the massless scalars will become massive once you take the loop correction. But the point is that, yeah, so.
For your purpose, you fine tune so that.
Yeah, exactly. So you do as much fine tuning you want and take them to be massless. Yeah, so this is parameterization for null vectors. You can check that p mu is 0. Okay, so this is a, suppose this is a d plus 2-dimensional null vector. Okay, and then this x is a d vector. X is, I mean, it is just x1, x2. I mean, this is all Euclidean, so let me just write x up to xd. So it's a d-dimensional Euclidean vector, and omega is a real number. Okay, so if you want to write the standard here, so energy is P0 is just omega times 1 plus x square. Okay, so that is the actually. So in this parameterization, so what happens is that now,
Sorry, Shamik.
yeah.
In that residue or whatever, EA is the energy.
No, sorry. This is the polarization vector
Oh, I'm sorry.
of the photon. Yeah, sorry. This is the polarization of photon.
But then I get confused. I mean, it's really polarization minus PK? I mean,
No. So sorry. These are dots. These are dots actually. These are all dots, but they are actually smeared out dots actually. Yeah. So these are all dots. Okay. So these are all scalar products between Q and D. Okay. Yeah. No. It's fine. Yeah. So now the thing is that so now let's take this limit. So now when we take this q0 going to 0 limit, so let us first define this operator SAX as limit q0 going to 0, okay, which is the same as actually omega going to 0, omega times OA omega x. Okay, so this q, actually I have just written this q in terms of this omega and x. Okay, and then let's take this limit. So let's formally define this operator. So this is called this leading soft photon operator. Okay. Now if you do this, so now you can actually compute what your q dot pk is. So pk you can, so p is like this, so pk for example will be like omega k, xk, something like this, and then you also have the q's written in that way. And finally, what you get is this nice form after taking this limit. So there is a q0 which comes from here, and then you take it to this side and take this limit, and finally what you get is SAX, and then I have this OI omega I xi is equal to sum over I qi x minus xi a by x minus xi whole square times this factorized form OI omega I xi. Okay. So now actually these things actually look like, well, I mean more like at least.
Sorry, I didn't understand.
Yeah.
From the lower line.
Yeah. So so there is a key q0 here. And now you define this thing. Oh, sorry. So this omega is actually, let me define this q0. This
And then you
Yeah, you also have to use this thing, the expression for epsilon dot, I mean, you have to compute what your epsilon a dot pk is using this particular
You have two polarizations.
parameterization.
Right. Isn't that right?
Yeah, yeah. So that's what this A stands for.
And okay, and then when you do x minus xi, where is that information on the polarization?
Oh, so that actually, if you compute this thing, and if you take this q0 to this side, then actually you get this one. Like there is an expression for this epsilon a in terms of this thing. I think well, I mean, in 4 dimension it is here. Probably write it. I don't know. So yeah.
A must be the
Photon. Yeah. So A is the polarization index.
Okay.
Okay. So that is basically the thing. So yeah, so there is an expression for epsilon a. So it's a function of q actually, right? So epsilon a q. So you take all these things, and if you compute this thing, then what you get is this. So the soft factor, and then you also take this q0 to this side and define this thing, which is sax, and then you get this nice form. Okay. Okay. So now. So usually what is done is that well, so there is some A here actually now. So let me actually work particularly. So I mean in well, let me work particularly. Yeah, I mean there is an x minus xi A here. No. So A is not actually the ZZ bar. So now I am thinking in terms of a d-dimensional A. So if you have like say d plus 2-dimensional Minkowski space, then they are in the vector representations of the SOD, right? So that's the case actually. Well, yeah, it is actually, because in so I'll be particular. No, it does actually, like in D, for example, so I'll be particularly working in small d equals 4, or basically the 6-dimensional space. So this will be SO4, okay, and there are 4 photons in 6 dimensions.
So distinguish basis of polarization.
Yeah.
Of the 4 objects. So distinguish basis is labeled by 4 dimensions.
Yeah.
Somehow is using x1 to do it.
Yes.
That's one.
Yeah. So this is just the vectors of the SO4. Yeah. Okay. Now.
So you're not in 4D.
Yeah. So you can do it in all dimensions actually, but I will be particularly working in 6-dimensional Minkowski space. Okay. Where like small d is 4, so this is actually a vector of the SO4. So SO4 is a little group. Yeah, so SO4 is a little group for the massless particles in the 6th dimension, and this is a vector of that actually.
Just out of curiosity, is there a particular reason you choose 6 dimension?
No. I mean it's just that I mean it's for my. So yeah, so the reason I don't choose. Yeah, no. So let me explain that. So the reason I don't do in d equals 2 or in 4-dimensional Minkowski space, because of some, I mean there is something actually in the sense that it's not well, it's a U1, so that well, the little group in 4-dimensional, so in 4D the little group is actually U1. Okay, so and the point is that these two, the positive and the negative polarizations, they actually transform in different representations. But once you go beyond 4, so all these things now actually form a complete representation. So that makes this thing easier. And the other point, so 4-dimension is a bit more complicated probably. Okay, so let me just do the simplest case actually that I can do. So you could say that, well, I mean, we could do it in 5-dimensional Minkowski space, but it seems that, I mean, these things are, I mean, because of this odd dimension, in odd dimension there are some issues actually. Okay, I mean this, I mean the thing that I will do.
There are some applications to 4-dimensional CFT.
Yeah, so I'll just come to that actually. Okay. Now the point is that, so now let me specialize to d equals 4 plus 2. Okay. So these are all SO4 indices. So this is a vector, and the point is that what one can show is that this SAX. So now, well, so now the Lorentz group SO5, 1. So that is the conformal group of the S4 or R4. So actually we are working on R4. So that actually helps, and the point is that what you can easily show that SAX, so that is actually a conformal primary of weight 1 and spin 1. Okay, I mean, so this just follows from the standard transformation law of the, I mean, the creation and annihilation operators actually.
Conformal field theory lives where?
No. I mean, there is no conformal field theory here actually. So this is just a rewriting of the massless thing.
Just to understand the algebraic thing.
Yeah. So you can actually basically think of, well, so this is the forbidden zone, but well, so I can think of the so you can think of this, well, this is in, well, for the time being you can think of this as living in the K space actually. I mean, not in the real space, or you can, if you are drawing the, well, if this is the Penrose diagram for the 6-dimensional Minkowski space, then you can think of them as living on the S4.
As the S4, and what is the algebraic statement that it transforms like conformal primary of?
Yeah, so this is the algebraic statement. Like,
what do you have to prove to show this?
oh no. So this is just the standard. Well, so I know how this OA.
Lorentz transformation.
Yeah. So because the SO5, 1, so that's the conformal group of the.
6-dimensional Lorentz transformation give you the whole.
Yeah, from 4 to 4.
Yeah. So I'm just talking about this X. So yeah. So in this case, actually, what is happening is that since it's Q0 or this thing, so Q0 is basically omega times 1 plus x square. Okay. So sending this to 0 and this to 0 are the same thing. So this is, you can think of this soft photon. It's an local operator on the S4 or the R4.
So firstly, you're using that if you've got a point at infinity, on the sphere at infinity, and you do a Lorentz transformation, it stays at infinity.
Yeah.
So
That is the point.
Lorentz transformation.
But actually, you know, so I mean, there is no scri plus scri minus here. I mean, this is just the standard. Well, I mean, the standard S-matrix. I mean, I'm just writing this in terms of this omega x.
Good. I'm just trying to understand, you know, just the algebraic thing.
Yeah. So this is the algebraic thing that the SO5, 1. Okay.
Maths
Or you can actually think in terms of the momentum space. Okay. So what is happening is that in momentum space, so the massless particles, they lie on this cone, right? And then you can take this cross section, a space-like cross section of this cone, which is an S4 or R4. And the point is that this SO5, 1, which is the Lorentz transformation in 6 dimension, so that acts as a conformal group on this S4. And just like AP or A dagger T, so these things, if P square equal to 0, you can think of them as staying on this cone. But now, if I take this Q0 going to 0 limit, so I get something which just depends on the x's. I mean, just the coordinates of one cross section of this cone. And the point is,
the projective cone?
yes.
So,
Yeah.
so you look at the action of the Lorentz group on the
Yes,
projective cone?
exactly. Yeah. But the point is that now actually I don't want to go into this because I mean this is just all the standard, I mean just rewriting of the massless thing actually. Not algebra of this A means?
This is an operator.
Yeah.
As an operator, it satisfies some commutation algebra.
Well, so this is a commutation algebra, so that is the algebra of this OA. So OA, so that is essentially the annihilation operator for a photon. So that's the whole thing actually. I mean, yeah.
This particular AC corresponds to some particular large gauge transformation.
No. I mean there is no large gauge transformation or things like that. So this is just a simple rewriting of this soft theorem. You can see.
From asymptotic symmetry.
No. I mean there's no asymptotic symmetry or these things now actually. So this is so this is just very standard. Just a rewriting of the massless thing actually. I mean there is no asymptotic symmetry or these things now
Let me
actually.
just say one thing that my head, okay, but may or may not be right.
No, yeah.
Which is that a massless vector, massless particle is labeled by a vector. It's light-like and it has some momentum.
Yeah.
So that vector has 4 directions. That's the sphere formula, and it has some net.
Exactly.
But
So
now
that's
we're
it.
taking omega to 0.
Yeah. So it actually lives on this.
So it's labeled just by this direction.
Yeah. So that's essentially this thing actually, and that's this cross section. And what this SO5,1 does is that I mean it will just map it into different cross sections, but SA. So under that, so these are all conformal transformations of S4 or R4, and under that, I mean just from the transformation property of this OA, you can show that this SAX, so that will just transform like a conformal primary of delta equals 1 and L equals 1. Yeah, so that I mean that you can actually show. I mean it is just some one line actually.
So I am not supposed to think about this as an asymptotic symmetry.
No, the asymptotic symmetries, all these things are not there actually now. So this is just standard. Well, I mean the standard quantum field theory. I mean for the rewriting of that actually.
Almost everything I thought.
But now actually, yeah.
Sorry, can I just ask and then please go on.
Yeah.
Okay, so I think I understand. You just take your photon operator.
Oh, so I actually this was already done. So I haven't even talked about what I have done, but yeah. Yeah.
You take your photon operator, you actor on it under the Lorentz transformation in 5+1 dimensions.
In 5+1, yeah,
And
suppose.
then
Yeah.
you look at how it transforms, and it
Yeah.
transforms when you take this Q0OA as the primary, right?
Yes,
Now
in
that's
this
correct, right?
particular
And
limit.
then
Yeah.
what was the only thing I didn't understand was the projective cone comment. Sorry.
Ah.
What?
Yeah. So I mean, you want to.
I mean, it's just the cone is a 5-dimensional space. You're looking at the point, cone, but modulo is length. So that's what, yeah.
Yeah, I mean that's what all it means actually. I mean there is
Sorry.
nothing more in it. Yeah. So this is actually a useful fact. Okay. In fact, the point is that let me, since I am just doing this thing, so let me also introduce the graviton. Okay, so this is a soft graviton.
And you do the modulo is length because you're taking omega.
Yeah.
The operator is really labeled by 4 numbers.
4 numbers. So it actually you can think of this as living on the S4 cross section. Delta equals 1 actually comes from here, that you are multiplying by Q0. I mean that's where this transformation law comes from actually. Okay, now let me also tell you, just introduce the GABX, which is a soft graviton. So it's a symmetric traceless tensor representation of the SO4, and the point is that this is also delta equals 1, L equals 2, and delta equals 1 is actually fixed because all these things there you get by multiplying by Q0. Okay, and that's how this picks up this delta equals 1. Okay.
All this has been known for 50 years or the last 3 years? It's also very interesting.
Actually, the point is that I don't think, I mean, this has been
Somebody knew it.
I mean, well, I am
Yeah.
well, like
So it's not some classic things you're doing.
I don't think
Okay.
so actually. I mean, this has not been looked at from this point
Okay,
of view
sounds very
actually.
good.
Yeah, just see. Yeah, so now let me just tell you that how this thing is done. And the thing is that I want to actually really show that this thing has probably some truth, in the sense that, I mean, if you really think of this as some kind of conformal field theory, maybe it has one extra dimension, which is the u, I mean the time-like direction, but it really behaves in that way actually. So yeah, all the soft operators. So they are the simplest thing to actually check or deal with, but then you can also have some other things actually.
And
But
then you have
those are,
continuum of operators which will take it now.
yeah. So that is one of the things.
I don't know, because this projective form makes sense only in the omega going to 0 limits, right? Otherwise,
Yeah, but the point is that you can have an extra direction, because if you are really thinking thinking about the hard excitations, they also see this extra u direction, which is this time-like direction actually.
So that's why you get a continuum of operators.
Yeah.
Field will be the continuum.
So every field is actually an infinite number of years. So that is one way to think about. But now actually I'll do the simplest thing, which is just this softly limit, where actually SA becomes a function only of the axis.
Four dimensions are probably field theory, and then you have a volume. You really have only 3 dimensions that problem.
Yeah.
So you will see all fields in some container.
Yes, yes, yes. It's exactly like that. So now actually we are talking about the simplest ones, which are actually dependent on x only. Okay, now this SAX, if you have this thing, so now what you can do is that you can, in 6 dimension, basically you can do this, apply this operator. Well, I'll just write xi, because this the fact that they also depend on this, I mean that, I mean actually nothing really, just assume that the xi will appear, and this thing actually becomes, it looks like a delta function, qi from delta 4 x minus xi times this y. Okay. Huh? Delta A. Huh? Delay. No, no, no. So this SA, so that's a function of x. So that's how you get this x's, right? And now you can actually see that, well, so now I can act with del squared delay on this.
Delay, you mean the A component of
Yeah, yeah. So delay, yeah. I mean, delay S is just delay. Delay. I mean, S is just a, I mean, so S is, so this SA, so that is a vector defined on S4 or R4, but R4, I mean, I'll be working with the R4 because that is, I mean, that is much simpler. Okay, and then you get which this thing, which is actually has the form of a word identity. Okay, and the point is that you could think of this, writing as delay some JA x, and then product of y equals this sum over I ui delta 4 x minus xi product over I, where this JA is actually, you can define as del squared of SA. Okay. Yeah. So it turns out, well, yeah. So that's the thing actually. So it turns out that it can be primary if you have actually certain restrictions. I mean, that's where this well, in this null states like things actually come. I mean, that's where I'll come actually. So now actually, so in this paper by Mitra and Kapek, what they actually observed is that this, if you just look at the soft factor, so the soft factor has actually a nice form, which is that it can be written as delay of some function, say psi of xi. Okay, or in the sense that, well, what they wrote exactly was that del A is b minus del b is a is actually 0. Okay, I mean, which is the same as writing this one. Okay, So now actually I will start from this point actually so that now actually suppose somebody gives you this thing. Okay, now I want to actually solve this, that I want to find out what my SA x times this quantity is. So that will be like what I have in mind is something like this, is that suppose you define the CFT or whatever it is, you define, suppose you define a CFT. Okay, by defining, I mean by telling that what the word identities are. Okay, like this will be part of the definition, but this will go there actually. So so you can actually start from this, I mean instead of this actually.
So
Okay.
O
So
also be a part of the CFT or
yeah.
But the
So,
word identities won't define the CFT code. You need extra data.
yeah, so I mean that's where actually I'll come. But the point is that in this case it turns out that you can actually solve this thing. Like you can't really solve all the, like you, well I think in only in two-dimensional conformal field theories you can actually solve for the correlation function of the stress tensor and some other fields in I mean starting from the word identity. And huh? No, well, so the JA, yeah, the question of whether it's a null vector, that does not actually appear. So JA is, yeah, so it's a vector of the SO4, well, but it's not a vector of the SO5, 1, right?
I'm asking because it looks like it comes out correctly.
Yeah. So I mean that's what it is actually. Okay, but the point is that so now actually what I want to do is that I want to prove this thing.
Are you asking whether del dot J is an element?
No, because it's a conserved current, then in CFT language, it also has a definite spin probably.
Yeah, so JA of course has a spin, so it's a,
Del dot J will be.
Yes.
delta equals 3, right? Delta equals 3.
yeah, so JA is actually delta equals 3 and L equals 1. I mean that's yeah.
Yeah. So now people think is that it's primary. That is this guy.
Yeah, so this is primary, but the point is that then this one actually has some issues, but let me actually come to that thing actually. So suppose
Also this omega is a bit of a weird thing, right? I mean,
omega y,
omega, your energy,
yeah,
is supposed to be some conjugate variable to delta. So this is not the standard diagonalization of the operator spectrum.
well, so the thing is that so if you just use the Lorentz transformation of this one, I mean which you know like how it transforms, I mean then you can see that I mean this will transform in the sense that, well, yeah.
For O's and S is the
Yeah, so this CFT,
these both there, Y's, which are your probes,
Yeah.
these other things,
right,
some omega non-zero. Now those omega, if you want to go to the conventional operator spectrum in which you have diagonalized the deltas,
yeah,
then you would have to some sort of take the Laplace transform by that, right?
yeah, probably, yeah. Well, so that is one way of, but actually I am not doing that. Yeah, so that is not exactly what I am trying to do. So basically the question is, yeah, so just 1 minute. So basically the question that we want to solve is that in D greater than 4, what happens is that like suppose I am in 6 dimensions, so I have 4 S-matrices, right? So because 4 soft S-matrices which are like SAX. Okay, but the point is that we have only one word identity. So I want to now solve this problem actually. So what like how do you go from here to here? I mean, you have this 1. I mean, so there is a mismatch of 3.
In my experience, in higher dimensions, the word identities don't determine the.
So in this case, I mean, they will actually. So I mean, I'll just come to this. Yeah. So in this case, I mean, it seems that I mean it does actually. Okay, so that is the problem. So what is usually done is this side. So you start from here and there, and but the point is that in this case it is much stronger in the sense you can start from here and go up to here. Okay, so and that is where this null, well, null state-like objects actually come.
Also, there is this statement, is there an operator statement in CSV? That is B minus ZBSA equal to 1.
Well, yeah, to the yeah, in the sense that I mean, if you insert this in the S matrix, then it is identically 0. There is no contact term or some sort of thing. Actually, I mean, it is.
With 2 of these games themselves.
I mean, yeah. So that is an. I mean, I'll come. I mean, yeah. I mean, that is a question. I mean, no. It is not actually. So you have to. I mean, you can look at these 2 soft particle outgoing, but I mean, it well. I mean, still it is not very clear to me. I mean, what is going on? But I mean, that is a very interesting question. So let us just look at this simplest case, which is this one, or there are. I mean, even in the case of graviton. So I have these basically the 9 S matrices, but we have this one. Like say, I have this GABX and this Y. Okay, and then I have only one word identity. Okay. So
that question is also word identity.
which one? Yeah. So you can also actually. No. The point is that. Well, so this is because the point is that the charge, actually the soft part of the charge, which you can construct also from the bulk construction, in the sense that I mean the standard, I mean the Minkowski space construction. So that, well, there is a function, suppose f. So for the soft photon, it will look like d4x, fx, and then del squared, del a, sa. So that's how. So that's why like. So this is the charge, and this is the natural combination, which you find, the soft charge actually. So if you write it in terms of the more standard way, the way I think Strominger wrote this thing, that in the sense you have these out states, and then you take the commutator of these things in. And you have some f's here, so this is equal to sum over I, ui, f, x, I, then this product over S matrices.
Just to understand, firstly, this word identity, this statement.
Yeah, so this looks like a standard word identity that you will use.
And you could derive it algebraically starting from that side?
Yeah. I mean, just take del squared del A. I mean, apply del squared del A.
Now you want to go backwards.
Yeah.
You already know the answer.
Well, but that but we will not use that actually.
You will not use that, but your test will be that you get back to this. That
Yes.
will be.
Yes.
You want to see whether there's enough information in just that equation with some structure.
Yeah, so that there is some structure. In fact, it is very interesting in the sense that I mean, you will see that I mean.
You just want to integrate it over.
Yeah.
Yeah, but the
Not
point is
solve
that
for that.
no, I want to solve for this from here.
Okay.
So that is a yeah, because like I have 4 S matrices, but just one word identity or. Well, so that is something which needs to be proved actually. So that's where I'll come actually. Yeah. So this is actually so the fact that del A SB minus del B SA equal to 0. So that comes from the soft theorem. But the point is that now you have to prove that this thing holds without using the soft theorem. No. So no. The thing is that no. The point is that suppose somebody gives you this thing actually, okay, say x, y x, some y x I, but you don't know like what this side is. So if you don't know, then of course you can't straightforwardly get. I mean, well, from this side, I mean that's what Prahar and this will get. But suppose you don't know what the soft factorization is or these things. But suppose somebody tells you that I have a conformal field theory. So basically, the input that you can basically think of in this way.
Once you know that if it is gradient, this is one equation for one variable.
Yeah.
Then you can just solve.
But the thing is that, and the point is that, so in this case it is, but in the case of the graviton, actually it is quite surprising that you get a form which is actually just like the super translation in the higher dimension. So, I mean, I'll come to that actually, but yeah. Huh? No, so I'll prove that actually.
Because you know from here.
No, but the point is that you don't want to use that actually.
Sorry, Shamik, so I think I misunderstood when you.
No, it is not just that. Actually, that's not TA. So you need some boundary conditions at infinity, and that's where this thing actually comes into play. That this is actually a primary operator of weight 1 and spin 1. Yeah.
Sorry, just to make sure, because I think I misunderstood when you first said it. So you're not really trying to solve for the correlators.
Yeah, actually, I am trying to solve it. No, I mean that's what I am doing.
That they are of this form. I mean that would still leave enough leeway.
No. Well, so that will prove the soft theorem from here actually, in that sense. But that is a different ball game. So it is actually some very small part of that you can think of.
Sorry, but since I don't know exactly what proving the soft theorem means, but in the end you want to just establish this relation.
No. I don't want to. So that well, like in the sense that if I could, then I mean that is a. But the point is that what will prove that I mean this thing holds, or in the case of GAB, I mean in the case of the graviton, something else actually holds, which is essentially. But actually, you will see, like in the sense that.
But you're not going to prove. You're not going to get more than this relation.
More than what?
For instance, can you get the result for the correlation of O? Can you do that?
That cannot be.
Of course not. Your goal is to get one.
No. Yeah, so I'll not, of course, get this, but what I will get is actually this one, but not this actually.
So you get less than that.
Yeah, so getting the whole thing, I mean, well, I mean that is.
There's no hope of determining the whole i's, right?
I think that's what Sanjit is asking. Can you get that O?
No, the thing is that what I have in mind is something like this. Okay, suppose somebody tells you that you have some sort of a conformal field theory with word identity for this E1 for this.
What identity would say this equals 0, right? Not just
No,
the
just word identity will say this equals this times whatever this, right?
Minus that is
This minus that is 0.
But you just have to impose, you would just say that the sum of all charges will be 0.
Just I mean, yeah. I mean, what do you mean?
Want to integrate over it.
Yeah. So actually, you want to integrate. So basically, suppose somebody gives you this thing that I want to define a conformal field theory with word identity for this infinite dimensional U1 symmetry. So you define the theory in terms of these things.
There's one current, right? I understand. One given current is what I did.
Yeah, but I like infinite dimensional in the sense that you can actually write it in this form. So this QF. So you can have this soft charge like this, right? Some d4x F and del squared del A S A. So for each F, like you have a charge. So you have like infinite number of charges.
What is X now?
Oh, F is the transformation function. So this is like the function which F multiplies some charge scalar fields there. So this is like the global transformation function. Okay, but now it's a function of X.
Wait, when you made a sudden jump. So far we had this word identity, which was clear. And like some people say, it's a word identity for one global symmetry in a conformity. Now where have you gone to with
No,
X?
so this is actually the form in, I mean, this is really the form which is more useful. But
But how do you go from that line to that line?
well, so this line to this line is a bit, but this is the thing which you get from the global. I mean, the way Strominger actually wrote this thing. I mean, that's the standard
That's some standard
word
thing, but
identity.
it's
The, like in the thing that your total Q is like your Q hard plus your Q soft. Okay, and the point is that Q commutator S is 0.
But from the logic that you were developing, it looked like we had one global symmetry in our conformity theory. There were no X. Where did that X suddenly come from?
Well, I could just integrate this with respect to F.
What I could do in a field is theory with one global symmetry.
Yeah. So this actually I'm not. Yeah. So you can actually just start from this and get this thing actually. So there is a certain jump in the sense that, well, I think in the case of S-matrix, standard S-matrix, it will be more useful to write it in this form actually. Okay. No, there is no jump here, but the point is that still it is, well, I mean, this is a more standard way of writing the symmetry. Yeah.
And that box equation over there is just a restatement of the ordinary soft scale,
Yeah.
right?
Yeah.
So,
I mean, suppose you have a U1 symmetry and an ordinary conformity theory.
Mm.
We don't say that it's infinite dimensional symmetry.
Yeah. So that is a bit, yeah, actually.
I know, but just he's developing from a certain point of view. From his point of view, it's still one symmetry.
Oh no, actually, yeah. So that is a bit, yeah, actually. So, yeah. So, yeah.
Why?
I mean, instead of using the statement.
No, it is actually.
Locally,
Wait.
giving
So let's start. Suppose I start from here actually. So let's just start. Well, so let's just start from here. I mean, which actually I should. I mean, and you get the same thing actually. So what you do is that you look at the transformation property of the both side under the Lorentz transformation, and that actually gives you the same thing, that this SAX is actually behaving like a conformal primary of weight 1 and spin 1. Well, actually there is some.
much more, right? Because we have a whole bunch of word identities.
No, but this point is that whatever be that, I mean, once you write, suppose, so yeah, actually the, well, so the way yeah, so it will take too long actually. I mean, if I, yeah, so.
No, you don't have to tell me, but just that, what is it? So,
The thing is that, no, the way I think about it is actually some, well, I mean, that I did not really talk about because I mean that.
it's fine.
Yeah, I mean, yeah, but suppose, so let's start from here actually. I mean, which was a standard way, I mean, more.
Can you go algebraically from your statement to that?
From here to
Yeah,
here?
can you go algebraically from there to there?
Yeah, I think you can actually, because I mean, that's how it is done actually. So basically what you do is that you have this SAX here, and then you can compute this thing where for an incoming soft photon actually, and then use the crossing symmetry to get this, and then yeah, then you have an I mean basically you have the S matrix here, and once you integrate, then you get this bracket actually. So this bracket is essentially, yeah, I mean you can get it from there.
People are saying that you take the first statement, multiply the f of x and integrate. Is that what you're saying?
Yeah, but the point is to get to these actually, so you should actually look at also the incoming softy. Like this is actually an outgoing, but you also look at the incoming, but then you use the crossing symmetry to connect this thing, and that actually gives you this bracket because this bracket, what it tells you is that basically Q when it acts on in states, and one of the Q's actually acts on out states. So that is actually one way of going this thing. But the point is that to do justice, actually, I think, yeah. So you have to like, yeah. So I can understand that why it is becoming so confusing, because I mean there is an introduction to it which itself will take that. I mean, well, I mean, which itself is.
Just go on along your track.
Yeah. No. It is fine, but yeah, I mean, yeah, I mean, this is very confusing actually. I mean, yeah. But the point is that so you could actually just start from here, or you could do this crossing thing to get from here to here. I mean, you will get actually get the same thing at the end of the day. And when they actually prove this when they go from the soft theorem to the word identity, they do it in this way. But what actually Prohad and they did actually, so what he said, well, I mean, he just interpreted this as a actually. So he did not exactly want to write it in this form actually. But the point is that I think, yeah, this form is actually more, I mean, it is a more legal way of writing this.
CFT point of view, if you just have a current,
Yeah.
right, then which is fun. So then this is the kind of word identity that you would expect.
This one, right?
Yeah.
Yeah.
And now in general,
But from the
general CFT, I cannot
S-matrix
do this,
point
right?
of view, I mean, this is more.
But for general CFTs, I cannot extend this to.
No. I mean, this is not a general CFT
Yeah,
like.
so is the fact that the current somehow is del square of.
And the thing is that I am not even really talking about a conformal field theory. So all these things are actually just SO5,1, but written in some fancy way actually. But I have not yet shown that. I mean, why that one should actually write it in that way. Yeah. So just let me. I think. Yeah. So one. I mean, probably. Yeah. Just let me finish this thing.
But where you go from a single symmetry to infinite dimensional symmetry. The thing that you are advertising saying that there is only one word identity, there are 9 components and so on. Actually, there are infinitely many things. So infinitely many word identities essentially, right?
Yeah, but the point is that I mean you will see. Yeah, but the point is that I mean if you want to solve that actually, the question is how do you get from here to here? Like somebody gives you this thing which you can actually get from here using this crossing and all these things. Suppose I mean this is a nice way of writing what I mean by the infinite dimensionally. And then my question is that how do you get this S-matrix of SAX and OI?
Let me make one point of this. What Shamik said, let me just say. He defined the CFT, let's say, in the future.
Yeah.
Because these are the light
Yeah.
versions.
Suppose.
There's also another CFT in the past.
Yeah.
And all the power and what Shamik and company do is some matching of the past and the future.
Yeah.
So there's more that goes in than just this. It's some statement that this equation for the future is the same as that equation evaluated in the past.
Just from the future point of view, it's
There's
not
nothing. No, I don't think.
Yeah, so this actually the fact, yeah, so it is not, I mean, that's why I said, like, the fact that this Q is actually a charge, like, it's a conserved charge and the Q commutated S is 0, so that requires some, this fancy, I mean, this anti-portal matching between this chi plus chi minus. So, yeah, so I'm just assuming that, well, I'm not going, well, I mean, if I go into that, then, I mean, yeah, it will take, well, I mean, I don't know how much will it take. Yeah, so just let me then just go through this. Probably, okay. So how much time? Maybe I just write down the answer.
One easily.
Oh, okay, one easily, okay. Then it's fine, okay. Yeah, so let me just steer this thing actually. Now the fact that Q, so you can write actually, so this charge as say Q hard plus Q soft. Okay, and these are all actually, let me write it as functions of F. Okay, so this has actually form which you can find out easily, which is something like say some before x, fx, and then some operator here which just comes from A dagger A. Okay, the creation annihilation operator for the hard particle actually Q hard. Now the point is that this has a certain transformation law. So if I call this U lambda as the unitary Lorentz transformation, which acts on the Hilbert space, then there is a certain Lorentz transformation property of this thing.
I hadn't understood your just the equation. QF is equal to QF hard plus QF soft. Just can you say what QF hard is?
Oh, QF hard is actually basically it's the part of the charge which is acting on the non-soft
And this charge
objects.
is charge in sense of point here. Charge.
Well, so this charge is just well, I mean, if you are just looking at the tree level theory, then this is just integral d3 p or d4. I mean, well, depending on which dimension you have a dagger a.
So charge under what? Charge of what? Just U1 charge?
Yeah, U1 charge, but you have an fx here actually.
Yeah. So say again, what is the charge under the large gauge transformation?
Well, so there is no. Yeah, so you can actually think of in that way, or you can just suppose I have a free theory, say half some del phi star del phi. Okay, so I can construct a charge, right, which is suppose some dnp, say some d mu p, then charge q or e, a dagger a, or and minus b dagger b. You have this charge, right? And now the point is that you can actually define a new charge qf by multiplying this by f. F is some function of p or x.
Isn't this the same as integrating the conserved current against f?
Yeah, I mean that is what it is. But the point is that if you just look at a free theory of charge scalars, you can actually define a charge, and the point is that qf commutator h is actually 0. I mean in the free theory. Okay, so there is no, well, so there is no notion of gauge transformation here because all these things are physical, yeah.
Okay.
Now the point is that now suppose I go to the interacting theory and I add, then I have to add this extra piece. So that is, well, I mean that is the way I would, yeah, so this soft extra piece, because what will happen in the interacting theory, because this by itself is not a conserved charge. Yeah, so now you have to add this extra piece actually. But now the way I would like to motivate this thing is that I know that how this thing actually transforms under this u lambda, right? And the point is that so if I want to add an extra piece to this, then it also has to transform in the same way as the q hard.
And what is u lambda?
U lambda is the, so this is the SO 5,1. So there is no fancy conformal theory here. I mean let's just do the standard S-matrix. So I am applying U lambda. So from this I know that how this QF hard actually transforms. And now I want to add an extra piece to this in suppose in the interacting theory. And then the point is that since, well, I mean they should have the same transformation under the SO 5,1, I know how this thing actually will transform. So now if I write my QF soft as integral over d4x f times some
And you get how that transforms just by keeping track of how omega.
yeah, I mean this is just yeah. So actually that gives you a transformation for f actually, in the sense that you get a QF prime hard.
Which is just f of lambda itself.
Yes, yes. In this case, but in the, when you go to the metric, I mean the graviton, so that actually itself transforms with some scale factor. Now, if you assume that this Q soft is an integral over the sphere of a local operator, then what you get is that this OX must transform like a conformal primary of spin 0, and so delta is 4 and L is 0. So that's the constraint I get. And now you can see that you can't have this thing actually, because if you now look at now suppose so say I want to think of it in the following way. Suppose somebody gives you all possible fundamental fields or whatever in your theory, and then you may try to construct what my OX is actually, right? Now OX I know, so it's a scalar, so it's a primary scalar of scaling dimension 4. Now the point is that, so the simplest thing, okay, so in this approach, the simplest thing you can, I mean, we will not construct, of course, Q. Yeah, so the simplest thing you could start with is that is
And you want to
SAX
make it entirely out of the gauge
out of the.
gauge work, the soft gauge. You are putting in that assumption.
Well, so we are also, well, we don't, well, the point is that I think the best thing will be to prove that you can have this unless you have this gauge. Yeah. But that is a very, well, I mean, we have not been successful in that direction so far, so we first start with this SAX.
So your assumption is you're building it out of the soft sector of the gauge.
For all the time I'm being. So this Q soft, so let me write, yeah.
So just before that, I mean, you gave an example of a free theory and how the sphere acts on it, and the fact that it's a symmetry of the free theory.
A free theory, yeah.
That presumably comes from the fact that free theory has a lot of symmetry.
Yeah, it does actually, yes, yes.
High spin symmetry.
It's
That is
a-
what
it's a-
is additional in free
I mean, is it a higher spin symmetry? I mean, this is just a local, well,
You have many conserved currents.
yeah, but this one is not, I mean, well, I mean, yeah, I mean, let's talk about, I mean, I don't think.
I feel that I think that is the only additional symmetry compared to the in addition to the conformal symmetry that a free theory has.
Well, it is a bit because in the point is that you can also have some kind of super translation in the free theory. I mean, which I don't think comes from the higher spin symmetries. I mean, that is not the same as this one actually. Well, so now let's construct this one term in the soft charge, which is this Fx. But now I am given this SAX, which is dimension 1 spin 1, and I want to construct a dimension 4 scalar primary, and the only choice I have is this actually, because I mean you can't have, I mean if you want to construct it out of the SAX, you have to write del square del SA. I mean that's the only choice. But now the thing is that this is not a
Why don't you write
primary.
del S the whole thing square?
Del A?
Del AS the whole thing square. Del ASA.
No. So this is one. Yeah. So yeah, but the thing is that I have that actually, but I don't think, I mean, I'll have the time to go into that. But so I mean, actually we have checked, and that does not actually work. So the first thing it works if you have three essays actually. The first thing actually it starts. So 2 actually will not work.
So SA squared.
SA squared. Well, that will not, well, so that has some problem. You need some dels acting on that, because otherwise charge conservation will not hold. Yeah. Yes, so just, so this is the simplest thing. Huh?
Sorry, SA was your delta equals 1 and equals 1.
Yeah.
The SA would be delta.
No, that thing is fine, but let's just start.
Yeah, got it.
No, but just square that.
A square. I think you want to.
Yeah, but
something with 3 words.
yeah, so well, no, 3 onwards means that the 3 I think is the first thing that starts working. So it is not just that you have to have delta equals 4, L equals 0. It also has to be a conformal primary, right? The point is
Certainly be a conform primary.
del A
S
SA,
primary even is single.
del A SA, del A SA.
No, just
You want
A to the power 4.
S dot S over.
No, but I'm so I'm just talking about a single
At the moment he's thinking this.
single SA. So now you have these terms actually. So you can add these terms and see, I mean, what you get. And well, I think you can do this exercise more efficiently than me, but this is the simplest thing. But now the interesting point is that this is not a primary. So it has delta equals 4 and L equals 0, but the point is that this is not a primary, and what you get is that now you look at the transformation of this thing. Say I make a special.
Exactly the null state, right?
Yeah, so now you actually make a Lorentz transformation of this, or whatever the conformal transformation of this thing. So you will see that this quantity is change. I mean the non-tensor part of this is actually proportional to del A FAB, where FAB is del A SB minus del B SA. Okay. So in order to have such a term as a candidate for the charge, so you have to have actually this quantity equal to 0. But you don't get FAB equal to 0, you get del A FAB equal to 0. Okay. Now the point is that you can set this equal to 0 because
This is equivalent to saying that del squared SA is a primary only when this condition is met.
yes, yes.
Okay, then it's, yeah. Because we know that once you have a primary, its null state is automatic.
No, but the point is that spin 1 is actually, but this, the thing which you are actually saying, so yeah, I mean that is a bit more complicated in the spin 2 case actually, because the spin 2 case, I mean they could not show that this J is actually a primary
Just
operator.
speaking to spin 1 for a moment, we know that if
Yeah.
you have a primary, then its null state is automatically there.
It's null state because of well.
So if del squared
Well,
SA was
wait. So the null state, so the null state, of course, we have not really defined any notion of norms or the things like that, but just
by the thing that is here.
yeah. So you have to set this equal to 0, and you can do that because this itself is a primary.
SA is primary, del square SA is primary, and then there is null state.
Right.
No. Del squared SA is not a
Is
primary
del squared
actually.
primary if this is true.
Yes. So that's essentially the thing actually.
Yeah. I think once you've shown this is just algebraic statement, then it's all.
Okay. So now actually, from in, but this actually still does not solve the issue because I mean we have not shown that FAB is equal to 0. But in this case, actually, it turns out that FAB is also equal to 0. And the reason is that suppose you construct this some kind of I mean just consider this quantity d4x FAB. Okay, so this you can write as I mean suppose I write this half some d4x del A AB FAB. Okay, so you can integrate by parts and then del A FAB goes, so you get a pure boundary term which is like say some d3s in a AB FAB. Okay. Now this boundary term is actually 0. That boundary term is actually 0 because the point is that we know that how this thing actually behaves at infinity. This quantity, this SA times whatever this is. So at infinity, as x goes to infinity, this actually behaves like some 1 over x square times some I a b x times some function, say psi b of x I plus the higher terms. Okay, so this follows from the fact that it is a primary of weight 1 and spin 1. Okay, and then of course what you get is that FAB is equal to 0, so it is Euclidean, so FAB must be 0. And that actually gives you that A has the form of a pure gauge, And the point is that, so this is very surprising because we have because this statement that this SA actually has the form of a pure gauge. So that is a statement which comes from the bulk, in the sense that from the, but we have not really introduced any kind of gauge
And this
redundancy.
now is going to be the large gauge calculation, right?
Yes. Kind of that. But the point is that we have, I mean, so far, I mean, there's no notion of gauge transformation here. So all these things are actually now, okay, so this is, so now let me do the spin 2 case, actually, which is more.
Just one quick question following up on something Abhijit said.
Yeah.
Firstly, SA by itself is a primary.
Yes, yes, so that we know from the fact that how these Q's transform, and then the thing is that I know that I have an SA, which is actually behaving like this, and
But
yeah.
when this condition is met, you're claiming del square SA is also a primary. So that means
Del squared SA is also a
by
primary,
itself is a
which is the same thing as saying that this del A FAB equal to 0, but then using the fact that delta, this SA is actually a primary of weight 1 and spin 1, then this actually equal to 0, this gives me the constraint that FAB is 0.
But it's also the same thing as saying that del square SA from normal point of view is
Yes,
null state.
yes,
Both
yes.
the descendant and a primary.
Yes, yes.
And then you're saying that also del A of del square del SA is, so it's null states upon null states.
Yeah, it's yeah. Actually, probably one can define some sort of norms and
Yeah,
these
yeah.
things. But yeah, I mean that I haven't actually tried
What you're
that
saying
thing.
is del square SA is not just a primary, it's a primary for a short term,
Yeah,
which has
yeah,
del 1 square null.
yeah. I think.
Okay.
But del square, say.
Yeah. So and the thing is that all these things you can.
Corresponding conservation equations for that. I mean, that's already the fact that del square is 0.
But if del square SA was a null state, it guarantees it's a primary. But it could be a primary for a long term. In which case it would not be any more, I think.
No, but just if I take my essay.
Oh, so let me. Okay, so you discuss. So let me just do write down the spin 2 case.
So is a constraint that it obeys. But wouldn't that already give me some, I mean, without actually going to the conservation equation?
Graviton. Oh, which is actually the most interesting thing.
If del square is equal to this
It's
equation.
an equation. Whereas it is a further equation.
Right, but that equation was not used when del square is equal to 0.
Ah, that's equation. Yeah, yeah. You're saying that, yeah. that is-
So actually, what I
del
have
square
used
SA
is
zero?
del square SA. No, that cannot be
I mean,
0.
it's a descendant and a primary. I should have said it's 0.
0, 0 why it should be 0? Yeah, so this null.
Unitary theory. Something
No,
like-
it is not. Yeah. So yeah, so that's why I said that. I mean, well, I mean the null state. I mean, quote unquote, all these things. But the fact is that this is a transformation from the SO 5,1 that I have some non-tensor, apparently some non-tensor quantities which have to transform, and then I need some things to actually go to zeros. But just let me just.
Yeah, it's just a null state. It's some, you know, if you allow null states that are not.
No. So these are not. Yeah. So these are not.
There's no norm.
I mean, let's not think about the conformal field theory. Yeah, so let's not think. Yeah, so the graviton, so there is this operator. So this is a soft graviton. Okay, so this has delta equals 1 and spin 2. Okay. So now, what happens is that you can now play the same game. So you have some Q hard plus Q soft. Okay, so Q hard you can construct in the free theory, and then you can think of this as correction which comes from the interaction correction from interaction. Okay. Well, and then the point is that you can get this, write down this word identity. I mean, if you assume that such an word identity actually exists, you have some omega I, QF, fxi out. Okay, this is the word identity. Now you can act with this u lambda and all these things, and what you actually get is that. So now, if I write q soft as some integral over d4x f, and then suppose I want to some operator say O x, then it has to be a primary of weight 5 because I have this E here, that's how it comes, and the point is that spin 0. Okay, and the point is that so you can actually play the same game here. That is, suppose I want to construct it with a single soft particle. Okay, then one of the candidate for this will be del squared del A del B OAB. Equation of no. Sorry, which equation of motion?
If I write down new charge with an arbitrary f, then you say that this is not conserved by itself. You need to add something. How do you know this statement? Are you using the fact that
That can be easily proved from just from the S matrix here. So well, so just the yeah. So let me finish this thing and then actually go into it.
He knows that the symmetry
That free.
extends from some other people. Now he's trying to see what's that possible extension can be using symmetry. Is that right?
how does he know that this quantity is a conserved charge?
He knows that it is.
No, I don't know. Actually, the thing is that I have not proved that this is a concept. So this is a much weaker statement.
Somebody's told you there's an extension. You want to find what a form could possibly be used from.
Exactly. Yeah.
That is as simple.
Yeah. So I have this operator.
I'm surprised that you have f without any index in this case now. Because I would
No,
have
no.
expected that the f will have some fa.
No. Actually, that comes from this thing actually. So what happens in this case is that if you look at the just if you just look at the free theory, suppose take any massless scalar field theory half del phi square. Okay, and then we know that the this thing, say suppose I want to write down some p mu, this charge. So there will be some d mu p, and then there will be some p mu a dagger a, right?
Yeah, so there's an additional index now, b mu.
Hmm.
And now what
Yeah, right. So that additional index, so if you write this as omega times f actually. So p0, so it has been, it is written for example like p0 is like e times this one.
yeah, so p0
Okay.
is one plus of conserved.
Yeah, but then p1, yeah, so p1, so that will be like e times some function f a dagger a.
Yeah, so you have the possibility of adding the different kinds of functions. I mean, just saying.
Yeah. So that's how you get this super translation. Like f can be whatever function you want, but the point is that if you take f to be of this very specific form, like say I can have 1 plus x square or 2x, or
So
like
you
1 minus.
has an implicit index a. Always
Well,
running the equation.
well, this q has an so this q in like q is f. I mean qf. You can think of this in this that way. No. Wait. So this f. So when f is for example as 1 plus x square. So this just gives you the e.
I mean, what I do normally is that if
Mhm.
I draw
Yeah, so in
a
this-
differential thing,
Yeah.
then I have this f mu and then del mu t mu at
Yeah.
the
Yeah.
bottom.
Right.
Where I have some f mu as against the large base term, where I just have a single function.
Yeah. No. So in this case, so this part. So in the free theory, let me just write this thing as qf. You can also think of this as the hard part of the chart as d mu p e f fx times a dagger a. Now, as you change this f, you get your P0, P1, P2, P3, and the rest of the things are the super translations. Because the thing is that in the massless case, suppose I will have this P mu. Okay, now I have written this P mu as E times 1 plus x square 2x 1 minus x square. So by choosing this f to be 1 plus x square, I get E, right? And then by choosing this f to be 2x, like 2x1, x2, x3, x4, I get my P1, P2, P3, P4. And by choosing this, I get P5. And then I can choose f whatever I want, then that gives my the rest of the super translation.
I think that for large
No, actually, yeah.
you would need a vector at
No, it is actually a it is actually a vector. So the way f will transform, like the SO 5, 1. So this thing will transform. These things will mix with each other. Yeah. So let me. Yeah. So is it clear?
I mean, I will still put that f to be that f thing.
This f thing. Yeah. So this. Well, so this by choosing different f. So for example, f equals 1 plus x squared. So that corresponds to mu equal to 0. Okay. Similarly, f equals 2x. That corresponds to mu equals I. So it is actually, but this, but under this u lambda or SO 5, 1 or what, SO d, 1, these f's will mix, and then you will see that, I mean, it gives you the, I mean, this. Yeah. So in this case, actually, yeah. So it is useful to write it in terms of f, and then the point is that you get this. You see how this f transforms under the SO 5, 1 or whatever. I mean, whichever dimension you are in. And well, so let me just finish this thing. So
One quick question.
yeah.
Derivative of photon operator.
Yeah.
When you take a derivative, does that derivative under this Lorentz group transform the same way under conformal transformations as derivative transform? Or is that something else?
No, I don't think. Yeah, it actually transforms in the same way. Same way. And the point is that we have actually checked it by checking with various. Yeah, I mean that's a very thing, but it turns out that, I mean, there is no issue with that actually. Yeah. Like otherwise, actually, we will not get any of these things. I mean, the point is that the fall-off condition at infinity. Okay, so in this case, so this is a potential candidate for this soft charge, and the point is that now you can play the same game. So this is actually a dimension 5 scalar, but the point is that it is not a primary. And the thing is that you have to satisfy. So you take so first time when you take this operator, just yeah. Okay. So the operator now, I mean, you can now do this special conformal transformation. And there are two things, two operators. So when you do this first infinitesimal special conformal transformation, the first thing that you get is the following thing. So which is actually, it's a non-primary. Okay, so let me write it in this way. Del A FAB is equal to 0, where FAB is del A VB minus del V VA, and VA as has been defined as, where VA has been defined as del B OBA. Yeah, sure. Yeah, and so this one is, and the second condition is this thing, that del squared OAB.
You should be, I mean, not to hurry you on.
No, it's fine. I'm just writing the answer. So del A del C OCB plus del B del C OCA plus 1/3 delta AB del C del D HCD is equal to 0. Okay, so these are the two conditions. So sorry, what is sorry. This is OCD. So these are the two conditions which you get. In fact, the point is that so this by itself, this is a primary operator. So you can actually set it to 0, and then it turns out that this object is basically, if you call this whole thing NAB, then this object is actually basically del B. Well, yeah. So this is actually del A NAB. Yeah. Yes. So now actually, so now you can actually solve this thing, and then what you get finally. So if you want to solve this thing, so you have to use these boundary conditions like this fall off conditions at infinity, and what you basically get after this is this constraint. The first one is that you can actually do it in two steps. The first constraint which you get is this. Of some scalar function psi. Actually, the point is that so this equation. So this is actually an integrated version of the some. This is actually an integrated version of Einstein's equation, the sphere component of the Einstein equations. Like if you look at the null infinity. And then finally, using this, you can actually now solve for this. So this equation, of course, can be easily solved, and its only solution has this form. Where f is some function. Now this is actually well, I mean, this has the form of a super translation. Which you get, I mean, just like in the case of the photon, we got that it's a pure gauge form like del A psi. So this actually has the form of a super translation, and this equation actually appears in a recent paper of Strominger and Rie. So this is actually an integrated this is actually an integrated version of these sphere components. By sphere, I mean the sphere at infinity, the sphere component of the Einstein's equation. So once these things are there, so now you can actually go back and try to determine that how you can actually solve for these S-matrices starting from the word identity. But yeah, but still, so there are some things to be done in the sense that, well, I mean, there are some integration constants. For example, this one turns out to be a fourth order equation. So you can, I mean, there are some integration constants which you can get rid of by using this the fall off conditions of these soft particles at infinity. Yeah.
This all of conditions was the same which gave you another way of doing gave you the soft.
No. This fall off condition is not that actually.
I mean, you're assuming these fall off conditions.
No. So this is the, well, I mean, this is the fall off condition in the x space actually. So this is in the fall off condition on the like on R4. I mean, the way you are doing. So if you think in terms of the S4, so this is the same as saying that, like, well, so S4 you can actually do it in 2 patch, and then the point is that how you actually. So that in the R4 case, I mean, that is the fall off condition. So this is not the asymptotic. I mean, this is not the asymptotic.
But it never found the set of fall off conditions with Strominger.
No. So this has nothing to do with that actually. So no. No. This is just the fact that if SA is a primary of dimension 1 and spin 1, then you get this thing. So what you do is that you do an inversion, and that actually gives you this thing. So this is just the S of 5,1 invariance of that. I mean, this has nothing to do with the asymptotic fall-off. But so in this case, so this is the R4. So this R4 is a cross section of the null cone. Okay, so it is that. So that is essentially that fall-off condition which gives you this. Yeah. So this is more or less roughly the very rough summary.
Last thing, it's occurring maybe I don't understand this yet. One thing very well, because I would have expected some.
Oh no. Oh, so.
Look like
Okay.
H mu equal to del mu epsilon.
No. So this is how actually, well, this relation. I mean, not this one actually. Actually, this relation which they actually got. So if you do this linearized Einstein's equation in harmonic gauge, and then if you do an asymptotic or the 1 over R expansion of that, the AB component of the Einstein equation. Now this AB should be identified with this sphere at infinity. So that has actually, if you integrate that, because the u direction is not there actually, so then actually you get an equation exactly like this, and this is the soft particle actually. So this you can see here. I mean, it actually comes as in, well, I mean, whatever, I mean, null or something. Probably I should not use the word null, because null is, I mean, we have not defined any kind of norm or things like that. Yeah. And that question, which is this F thing was there, right? I mean, F. So
Yeah,
that.
it appears that you are writing everything in terms of the same scalar.
Yeah. So this. Yeah. So that is this form. Like, I mean. Well, so yeah, I mean that's so. Let me write some shy tilde here.
Yeah, I would have expected the killing form.
Well, so that is not an asymptotic symmetry as such.
So it could be a, even large diffeomorphisms.
No. But the point is that the asymptotic symmetries are specified by this one. I mean, the super translation is specified by one function, right? No. I mean, this is a standard, like.
Yeah, it's not standard enough for me.
No. But the thing is that if you just look at this BMS4 standards, I mean, I think that is u going to u plus f z z bar.
Right vector
Yeah.
as some kind of.
Yeah, so that I can explain actually now. I mean, I mean that is the thing that.
Maybe we can explain it at the last stage.
Yeah, so that but that actually you can just yeah. I mean, if you take, I mean, as you change f, like you can take like 1 plus x square or 2x, 1 minus x square, and then whatever you want. That actually gives you all the p's, p news actually. Oh yeah, so these are, I mean, there is no subleading here actually.
So if I start with electrodynamics,
Yeah.
instead of gravitons, electrodynamics, what I am understanding is that if I get a word identity in the form and I assume existence of a charge in which your SA enters linearly.
Yeah, so that is the simplest case, but then as he said, I mean, you can take 2 essays and check, I mean, whether you get a, or 3 essays.
I am asking that question.
Yeah.
When you have subleading soft theorem for
Yeah.
electrodynamics, you need the divergent charges. In some sense, you can understand them by taking divergent charges.
Oh, okay, the charge constructed is divergent.
Yeah, from the.
Well, so as far as I know, the point is that these subleading theorems, which well, I mean not the, but the subleading soft photon, right? I mean
Yes,
whatever.
yes.
So that is not a local. I mean that is not a standard symmetry, right? I mean that is something non-local on the light cone.
Either you look at it as a non-local theory or as a local.
No. I mean that is not a standard symmetry, right? Like it depends on, well.
Still, you can get it from forming just like
No, no, see that is a machine, like, I mean, the point is that you can take any theorem and convert that into the word identity, but the point is, and well, I mean, Strominger actually mentioned it very clearly that, I mean, it's not a local form actually, so the charge or what,
Follow up conditions, but nevertheless you can get that. So I had the question that in this analysis, if
see, in this
try to-
analysis, all the things are actually local. All the things are actually local in the sense that, so you can actually look, if you even just look at the free theory, and then you can see. So in that, I think it is this, you were talking about this low subbuildings of theorem or something. Yeah, so that has this, yeah, I don't know actually. So that
So your analysis, if it is repeated for that word identity,
that will not work actually. I mean, that
Not work?
would not work. Because the problem is that, so that is a very non-local object. So the word identity which you get, if you write it as a word identity, so you don't really get a thing which localizes on the sphere. So you get some integrals on the time, I think. So that is not a standard. So you can't actually apply that to that, because I have suppressed the U direction, and that is because of this local nature of this thing. Because if you write this, I think if you write this subleading theorem, you will get some integral over du also. U is the time.
that gauge parameter does not depend on UC. Okay, fine. Maybe that is the point that we cannot apply this analysis.
But you know, probably some version of this will apply, but I don't, like, the point is that, I mean, this is, well, I mean, this is, well, here there is no explicit mention of U, because all the things actually localize on the sphere. But in this subleadings of theorem, yeah, that well, I mean, that is not a at least not a standard, very standard thing.